Okay, so today we're going to talk about the MiniMax algorithm. So before we dive into that, I'm going to quickly just review the idea behind uninformed searches because that really forms the backbone of MiniMax. So let's start with breadth first search. So in this algorithm, we started a node and then we search its children. Then we search the children of that node that we just searched, and we continue that process. So to describe this a little more algorithmically, let's have a data structure that keeps track of the nodes that we have to search. So in breadth first search, this is called a queue. What a queue is, it's first in, first out. So what that means is if we see node 1 and then we see node 2, that means we'll search node 1 first, then we'll search node 2. Okay, so now there's a subtle difference between seeing and searching. So like in this example over here, let's say we're starting in node 1. So we have seen node 1, we haven't searched that yet. Once we search node 1, we will see node 2, 3, and 4 because those are the children of 1. Once we search 1, we can see its children. Okay, so let's go through an example of what breadth first search is so you understand better. So to search, right now we have 1. Now we want to search 1. So we remove 1, we search it, and we add 2, 3, 4 because we just saw them, so we add them to the queue. Now we added 2 first. So now we're going to take 2 out of the queue and we're going to search. We've searched 2 and we get 5, 6, and 7. So we add 5, 6, and 7 into this. Then we remove 3. So we've searched 3 and we get 13. Then we search 4 and we get 14, 15, 16. And we keep doing this all the way till the end till till our to search is completely empty. Once to search is completely empty, we've searched everything. Okay, I'm not going to go through the entire example just to save time. I feel like that gives a good enough idea of what breadth first search is. Now let's move on to depth first search. This concept is very, very similar to breadth first search. The only difference is instead of a queue, we use a stack. Now, a queue was first in, first out. A stack is first in, last out, or last in, first out. So it's basically just the opposite. So in a queue, if you saw 1, then 2, you would search 1, then 2. With a stack, if you see 1, then 2, you search 2, then 1. That's the only difference between breadth first search and depth first search. It's otherwise the exact same thing. So let's just run through, well, not the entire example, just a part of this example to give you an idea, to give you a better understanding of what this is. So in to search, we have 1 right now. So we search 1, remove that, and then we add a 2, a 3, and a 4. Now we just we added 4 last. So now we're going to pop 4 from this. We've searched 4, and then we add 14, 15, 16. Now 16 was added last. So we remove the 16, we've searched 16, and we add nothing else. Then we've searched 15, and we've searched 14. We haven't added anything else because they would just leave nodes. Then we pop 3 from this. We have searched 3, and we add 13, and then we search 13 because that was added last. So essentially, when we look at breadth first search, you see that it goes layer by layer. First we do all of these children, then we do the next layer, and then we go into the final layer. Whereas in depth first search, we go down the entire tree to the end, then we go down the entire tree to the other end and keep doing that. So it's basically just going down the tree, and breadth first search is doing it layer by layer. Then there are other types of searches like you have depth limited search, which only searches a few layers in a tree. So you only go to a specific depth. It can be useful in games. You have iterative deepening search. So you go to a specific depth, and if you don't find what you're looking for, you can increase the depth. It seems counterintuitive because, like, why would you search to a depth and then search again, increase the depth and search again. But since like trees grow exponentially, um, it can be computationally more efficient to not have to search that one extra layer. I won't go into detail about that, but just thought it was interesting. Anyway, so A-star search it's like breadth first search or depth first search. The only difference is you don't use a stack or a queue. You use you define your own data structure, and and that decides on what node you should go to next. So you can think of it like an example would be, think of a map. You have to go from point A to point B. Actually, let's draw that out. So you have to go from point A to point B, and there are several other points that you could potentially go to. But you could have a heuristic that says that go towards the point, like search the point that is in the direction of the point you have to go to. So instead of searching this node or this node, the data structure would tell you to search this node. So it can just be computationally a lot more efficient than breadth first search or depth first search. So yeah, that's that. Anyway, let's move on to the MiniMax algorithm. So MiniMax, it's an algorithm that it's a brute force algorithm. It evaluates all possible game states and then chooses the best action based on that. So for example, let's say you're playing cross and knots, tic-tac-toe, whatever it's called, this game. I think it's called tic-tac-toe. Yeah, so you're playing tic-tac-toe, and so at the start you have 9 possible moves. You can put a cross in any of the 9 places. So that first node has 9 children. Then at that first layer, the first layer that we generate, you can put a circle at 8 different positions, because you have a cross at 1. You can put a circle at 8 different positions. So the branching factor for every node in that second one is 8, and so on and so forth till you reach the end game states. So yeah, so MiniMax would evaluate every possible game state that you can be in, and based on that, it would pick a move. So when we run through an example, that would make more sense. Sorry for that siren. I don't know if you could hear it. Anyway, so let's say we have 2 players, right? We have orange and we have red. Orange is a max player and red is a min player. That means orange is trying to maximize the score. We have scores at the leaf nodes, 5, 2, -1, 8, 4, so on. And min player is trying to minimize the node. So yeah, self-explanatory. So as we see, it's orange's turn first, right? So now orange makes this entire game tree, so it can make 2 moves. After it makes, let's say, this move, red can make 2 other moves, and so on and so forth. So that's how it makes the game tree and comes to these end states. So over here we have a 5 and a 2. Now we have a red over here. It's red's turn, right? So that means red is a minimizing player. So red would choose to go to 2, right? So the score, let's change the color up a little bit. So the score at this node would be 2, because red is a minimizing player. Since it's the red's turn over here, it will choose the end state that minimizes the score. Then over here, red just has 1, so the value is -1. Now this is a max player. Orange is a max player. So over here, it can go to this state where it knows it'll be 2, because the minimizing player will choose 2. It can go here, which is -1. It can go here, which is 8. It will go to 8 because it's a maximizing player. So the score over here would be 8. Similarly, red over here is a minimizing player, so it would choose 1. Orange has no choice, so it would be 1. Red, minimizing player, it would choose 1. So the score at this node over here is a 1. Now we do the same thing on the right side. Now red is a minimizing player, so it would do a -4. Orange has no choice, so -4. Orange has no choice, so -5. Red minimizing player, -5. Now it's orange's turn. Now, since we have propagated all of the final game states up, we can choose, okay, so it has a choice of either getting 1 or -5. Of course, it's going to choose 1. So in this case, after running MiniMax, orange would choose to take the action on the left because it has a higher expected payout. Now, of course, this is assuming that the other player is also playing to the best of its ability. So that's what MiniMax is. It's a very simple algorithm. There are slight augmentations to MiniMax that are used in games. So because games have extremely large game trees, like this is a really small tree, but for something even like tic-tac-toe, it would be enormous. So something like chess has, I think, 2 to the power of 35,000 possibilities, and that's just an unfathomable number. Like, that's not something we can compute realistically at all. Like, no one understands what 2 to the power of 34,000 means. So instead of reaching like an end state, you can run MiniMax to like a certain depth and then use heuristics to evaluate the score of those nodes. So it's not an end state, but let's say I'm playing, it's my turn, and I look like 3 steps into the future, so that's just 3 layers. I can say, okay, this game state has a score of like 80 because I have 2 horses in these positions, but this game state has a score of 100 because I have a queen and a horse right next to his king, something of that sort. So you can use heuristics like that to evaluate game states, like midway game states. Instead of breadth first search, you can use depth first search, so that'll just look at an entire game tree, and a bunch of different things you can do with MiniMax. Go is another game which is, I think, orders of magnitude more complex than chess, and it was actually really interesting how AlphaGo evaluated the game states. It was kind of like it showed creativity and made moves pros couldn't understand till like a few moves later, which was really interesting. Yeah. Anyway, so I know at the start, like, learning about AI can make it seem like it's trivial and boring compared to like the idea you initially had of what AI is and how it works. But just these simple but really brilliant and elegant ideas can be used in creative ways, with various tweaks, to perform just phenomenally and actually showing something that we might actually consider intelligence. So yeah, I think that's it for this video. Yeah. See you guys in the next one.